Okay, so let's finish this off. So now we're at step 8, which is to essentially just invert the matrix and solve for the I vector. Okay, in the last class they asked me about the underlines. It's an old style of notation that not too many people use anymore, where we used to, the number of underlines corresponding to the dimension of the matrix. So I with one underline is a vector. If I was talking about the admittance matrix, I would call it Y with 2 underlines because it's a 2-dimensional. Don't have to worry about it. Okay, so let's go ahead and solve. So what we are left with is V1, V2 is equal to the inverse of the Y matrix times IA negative IB. And if we wanted to, well, I'm not going to talk about manual inversion of the matrix, so I'm not even going to discuss it. And so what we would do is use the calculator to invert this. So that's nodal analysis in a nutshell. And then it spits out your V1 and your V2, and you're done. You get all your values in one package. The difficulty is predominantly with setting up the matrices, and once you do that, solving is relatively easy. Okay, so let's see where we go from there. Bring my notes up. Now, the real value associated with this is when you get to larger and larger systems. The difficulty of doing this is, let's say, maybe a wash when it comes to doing 2 or 3 node systems. When you start getting to 5, 6, 7 node systems, that's when it becomes easier to make the matrix and solve using your calculator than it would be to go through all that, using the parallel and series combinations in order to solve. All right, so next thing we're going to do is let's talk about the admittance matrix for a second. Okay, what are some things that we can take away from here? So, unfortunately, I have to go back and forth. Why don't you guys throw out some stuff? What's some stuff you observe? Obviously, the fact that it's square is one of them, right? What about the diagonal versus the off-diagonal elements? So the diagonal would be this part of it here. So the diagonal elements tend to be positive, right? And they also tend to have more components to them, right? The off-diagonal elements tend to be negative, and although we don't have a very big matrix to illustrate whether this is true or not, they seem to be, yeah. Yes, which implies symmetry, right? It will be for the base case of the admittance matrix. When we get away from that is when we start having dependent sources. So when we start getting to dependent sources, that will break the symmetry of the Y-bus matrix. But for now, we can consider it to be symmetrical. So that's really the main takeaways. It's square, yes.
Would the delta Y thing itself to convert it into parallel and series circuits?
No, you will not. The delta to Y conversion, I mean, you don't need it for this because it doesn't have any bearing. It would just be a delta, type of configuration inside of a circuit. You would just label those nodes. Yeah. The nodal analysis and mesh analysis are both very much, especially once we get to by inspection, plug in the numbers and solve it, and it's completely done. Okay. So let's write down a couple of those observations that we had. All right. The off-diagonal elements are equal. Which implies some sort of symmetry. The only adjacent branches show up in coefficient for no decal. Okay. Only adjacent, and I'm going to explain what this means in a second, because this is what we're doing is we're slowly leading up to the inspection method. So we're giving ourselves the clues that we're going to use. Only adjacent branches show up in a given row / equation. So what does that mean? Let's go back here for a second. Right here, the first row is analyzing node number 1, right? So that means that we expect only these adjacent elements to show up in that first equation and in that first row. R1, R2, IA. Those are the three adjacent elements to node number 1. R3, if it were to show up here, right, that would be something for you to question and say, okay, well, I may have made a mistake here because only, and that's what that second bullet means, is only adjacent elements should be showing up in a given row. Row number 1 corresponds to node number 1, and then, et cetera, et cetera. Does that make sense? Does everybody understand what I mean? Okay, good. Sometimes I spend too much time explaining something, and you guys are like, okay, we get it. Move on. All right, next. Diagonal elements are positive. And off diagonal are negative. So now getting back into this and taking a real close look at it, why is it, let's just compare the yellow and the green, okay? The diagonal and the off-diagonal element for the first row. So you'll note that the diagonal element simply just contains 1 over R for all of the adjacent resistances, right? It's 1 over R1 plus 1 over R2. Same thing if you look at the diagonal element for the second row, it's 1 over R2 plus 1 over R3. Right? So the yellow and the purple, that's a sum of all the admittances that are adjacent to the node. The off-diagonal is only one admittance because it's the admittance that separates the two nodes, right? The place 1, 2 in the matrix corresponds to the resistance that separates nodes number 1 and nodes number 2. So the diagonal elements contain all adjacent branches the off diagonal contain only one that connects the two nodes. And then lastly, the known currents are positive if entering the node, which is something we've already talked about before. Going back to this right here, that's weird. In the beginning, if we were to have used a positive value of IB, meaning we didn't do KCL, so everything was heading into the node, what would have ended up happening is the sign of the whole second row would have been flipped. Okay? Which is fine for solving. It would have given you the same answer, but our rules, quote unquote rules that we're trying to set up about the admittance matrix, they wouldn't have worked because the off diagonal elements would not have all been positive, et cetera, et cetera, et cetera. So you can kind of see what it is that we're trying to do. We're trying to do it in a specific way so we can predict the way the admittance matrix is going to look, so we can move on to doing this by inspection, which means that we no longer use the equations and we just come up with it. Okay, so now Y-bus is just another name for the admittance matrix. Sometimes we call it the Y-bus matrix. Actually, I'm going to be consistent. I'm just going to I'm not going to use that. Okay. So, let's draw out a more detailed, yeah. I'll let you guys look at that for a second. Okay. Any questions on those bullets? The wording's not perfect. It's more of just a, yes?
Will that matrix always use a square matrix?
It will, 100%. Always. That's one rule that's never going to change, regardless of dependent sources or whatever might be involved. It's always going to be square. Yeah. Yes. Yes. We're going to look at some bigger examples where those relationships will be even clearer. Yeah?
Will the dimension of the matrix always be the number of nodes minus 1?
Yes. That's by default because you have the number of nodes, you make one the reference, so it's always going to be n minus 1. Yeah. Always square with size of n minus 1. Okay. So now how do we generate the matrix, the admittance matrix by inspection. So let's say we have a system. First thing that we want to do is we want to generate, and actually we're going to generate all the matrices and the vectors. So let's do the I vector. So this here is going to be the sum of all current sources heading, flowing is a better word, flowing into node number 1. Okay? Then we have the sum of all the sources flowing into node number 2. Sum node number 3. Okay? And then it keeps going on down. So that is our I vector. All we have to do is look at each node that we've determined and get the value of the current sources flowing into that node. If there is no current source connected to the node, then that value will be 0. So that's fair game. It can be 0. Okay, equals. Now what we have is the Y bus matrix, or the admittance matrix. So we have element 1, 1. And for the purposes here, we will assume everything is in numerical order. There's nothing that says that node number 1 needs to be the first row and node number 2 needs to be the second. If you wanted to make it really difficult for yourself, you could just scramble it, okay? But we're going to assume first row corresponds to node number 1. It prevents us from having to come up with a whole other set of numbers. Okay, so it's going to be, the value here is going to be the sum from k equals 1 to the total number of nodes of plus 1 over resistance between node number 1 and node number k. Okay? And this will be for all adjacent branches. Right? Meaning that if there is no resistance between node number 1 and node number 70, that resistance is not included in the sum. And so what would that give us? Right? That gives us 1 over R1 right, and this is just an example. This part. There may not be an R12 or an R13. Okay, now let's move on to element 1, 2. So we're almost done here, right? Okay. We'll do element 1, 2, and then we'll stop, and we'll pick up from there. So real quick, element 1, 2 will be equal to the sum from k equals 1 to n of negative 1 over r1k But we hadn't done it all yet? First two, okay. So, what we're trying to do is generate the Y matrix by inspection. Couple things. We know that going down the diagonal, which is this, right? There's one way to define the values. And then the off-diagonal elements, which should be symmetrical, meaning that this is equal to this is equal to this, should equal one another. All right, so let's talk about how we come up with the individual elements. I think we already talked about element 1, 1, which was simply just the sum of the conductances, or 1 over the resistances, for all those adjacent to the node. So you see we have a sum from k equals 1 to n for all adjacent branches, 1 over r1k. So k is going to count up, it's going to give you r12, r13, r14, r15, etc., etc. If there is no connection between 2 points, let's say there is no resistance between points 1 and 6, what is the resistance going to be for that? The resistance is infinite, right? Therefore, 1 over that resistance will give you a value of 0. So it won't even come into play in the calculation. So that's one way to justify the way that is structured. The off diagonals, right, are simply going to be minus whatever the resistance is between the 2 elements. So this is box 1, 2. So we're looking at the resistance between nodes 1 and 2. Now, why do I have it written in this way? 99% of the time, it's just going to be one resistor. However, there could be a case, like what I've shown up here in the green, where there's multiple resistances between the same 2 nodes in a circuit. In that case, it's going to be minus the equivalent resistance there. And that means that we would have to find the parallel resistance of the R12A, R12B, all the resistances that connect 1 and 2. But that's probably going to come into play less than you would think. And so 99% of the time it's just going to be minus R12. And actually, there's a mistake here. Because I forgot one thing. It's 1 over. Same thing here for R13. And then it keeps on going to the right. Now if we look down at element 2, 1, which is right here, it should be the same as element 1, 2, because symmetry applies. Symmetry will not apply in some cases, specifically when we have dependent sources. But when we only have current sources, independent current sources present in the circuit and resistances, symmetry applies. Now, we can rattle through the rest of these relatively quickly. We have element 2, 2. You're going to see that's again just going to be the sum from k equals 1 to n of 1 over r2k, right? 2, 1, 2, 3, 2, 4, 2, 5, etc., etc. Notice that in here, I will, 1 second. This will include the resistance between the node 1 and the reference node, or whatever we're considering the ground to be. Well, I'll say reference node. 1, 3? Okay. Element 2, 3 is going to be one over that. Element 3, 1 is going to be the same as 1, 3. Element 3, 2 is going to be the same as 2, 3. Right? This one, and then element 3, 3 is just going to be another diagonal element. Right? We're not going to go through and define that again. So the basic idea is that along the diagonal, you have a positive value that's going to be the sum of multiple resistances for all the adjacent elements. Any resistor that touches that node. The off diagonals will most likely, more times than not, just have one element. It'll be negative 1 over the r, that's I to k, whether it's 1 to 2 or 1 to 3. We have considered the case where there are parallel resistances between the two paths, but that's going to be less likely. And also what you can do, if you don't want to incorporate that into the nodal analysis, you can go ahead and just simplify the circuit beforehand. Right? If you're given a circuit where you have multiple paths between two nodes, you could just collapse them down, redraw the circuit with a single resistor there, and then you wouldn't have to worry about this. And then lastly, we have to have our unknown array of voltages, which is simply going to be voltage V1 to Vn. Or sorry, Vn minus 1. Okay. Yeah. To where?
There.
Okay. I'll leave it here for a second. For this material, I know I keep saying this, but it's again true for this chapter. Practice, practice, practice is really the only way that you can get a handle on this. And we're going to do a lot of different problems. So you'll have a lot of opportunities in your homework. You'll have a lot of opportunities here in class in order to practice. Okay, so we don't have much time. But I do want to get through this example since we did it in the previous section. That'll get us caught up, and then we can move on to the quiz. So this example is using nodal analysis for circuits with dependent sources. So how do we do that? Just like our previous the way we introduce nodal analysis, period, we are going to introduce this using an example. So let's say we have a circuit with a dependent current source, R13, R12, R23, and a known current source, IA. Okay? How are we going to solve this using nodal analysis? First step, like usual, we label everything. Although slowly we're going to have less and less of a need to label things. Because as we start just referring to everything using double subscript notation, which is based off of the node numbers, we don't have to label every voltage, every current. Like, we know that I31 is this current, I21 is that current. We know that V13 is this voltage right here, et cetera, et cetera. The one place where that's not true is we do have two potential values of I23 because there's two paths there. So I've labeled this I23 prime. So everything's labeled. We set our reference. V3 is going to be our reference. I'm going to post these notes online because I know we are going to go through this a little bit quickly, so you can take a closer look at it later on. So even though we know that this is not going to work, let's try generating our admittance matrix by inspection. Okay? And then we'll see what differences there are when we that result from the presence of the dependent sources. So let's see if I can get both of these in the screen. Now I know the values are already shown, but let's go through and talk about the methodology behind it. The 1, 1 value will contain 1 over the sum of 1 over all the adjacent resistances. So the two adjacent resistances, the resistances that touch node number 1, are this one and R12. So we have 1 over R12 plus 1 over R13. It's positive. It contains two elements because there's two resistors that touch node number 1, right? Element 1, 2. First off, it's going to be negative. It's going to be 1 over the equivalent resistance between node 1 and node 2. In this case, like 99% of the cases, there's only one resistance. So we have negative 1 over R12. Symmetry applies. So again, we have negative 1 over R12. And then lastly here, for element 2, 2, what are the adjacent resistances? R12 and R23. Those are the ones that touch node number 2. We don't have to worry about node number 3 because we know that the voltage there is equal to 0. Okay, now, but let's, in order to really analyze this, we're going to have to go back to doing it the way we originally did, which is using KCL for the two nodes. So one of the expressions here is going to handle node number 1, which has I21, I31, and the dependent source summed together. And then the other one is node number 2, which has the independent current source, I23 prime, and I21 summed together. We're going to move the constant current sources to one side. In this upper equation, we don't have any constant current sources, so that will be 0. We're going to substitute for Ohm's law. So I31 will become V3 minus V1 over R13. Remember that the double subscript notation tells us which comes first, which comes last. I31 means current flowing from node 3 to node 1. When you convert that or you substitute using Ohm's law, that means it'll be V3 minus V1 over the resistance. V3s go away because they're equal to 0. And what we're left with, when we collect the terms by voltage, is something that looks like this. This should look familiar, this should look familiar, and this should look familiar. With the exception of the signs being off, which we could fix by multiplying this first equation by -1. This is our 1, 1 element from our previous Y matrix. This is our 2, 1, and this is our 2, 2. So those stayed the same. However, when we collected by our voltage, we see now that our 1, 2 element is different. So symmetry is broken. And the reason for that is because the dependent source mathematically looks like a resistance, but is only going to be reflected in one of the off diagonals, not both. So anyway, we take this equation right here, we convert it to a matrix form, and you'll see that one thing I did do was I switched the signs. I multiplied by -1, so it looked closer to the way we're used to seeing it. And For the first KCL node, there is nothing in the I vector because we don't have an independent current source flowing into node number 1, only dependent. So anyway, we get our form like this. We know all the values here. We know all the values here. And then we invert. Well, that's the difference. And then lastly, in order to finish, we would invert this matrix, multiply it by this, and it would spit out our V1, V2, which again, the inversion we're not really gonna dive too much into. So just get familiar with how to do that in your calculator. Most definitely, by the time the next quiz rolls around, you want to be comfortable doing that. So I know that was a quick overview of this, but we'll go through tons more problems, and I'll post this online. You can take a closer look. But it's really nothing you haven't seen before. It very much. All right, so 2 ohms, IA, 6 volts, 2 ohms, 2 ohms, 2 amps, 3 ohms, 6 volts, 4 ohms, 2 ohms. And then lastly, we know that the voltage across here is 4 volts. Okay, we can see everything? Good. So how are we going to solve a problem like this? We don't really have, it's not as simple as we usually have circuits where it's like one long line, and so simplifying down is a little bit of an easier process. It's a little bit more straightforward exactly how we're going to proceed. For this one, it's a little bit less clear. There's a lot of different ways that we can take this. So here's what I would suggest for problems like this. There's a generic way of doing it. A generic way, which is going to look really messy, is to write down all the equations you know and try to combine them using algebra in order to solve. That's a really vague and generic way of doing it, and it requires some sort of intuition on how to combine the equations. Also, when the circuit gets bigger, it becomes a lot harder to pick out which equations it is that you're going to actually use. Another way of looking at it is simply just to try, so step 1, look for, and I'm going to say by inspection or just by eyeballing it, equations with only one unknown, and solve, boom, 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 then repeat. And so a lot of that we can do just by taking a look at the circuit right here. So first things first, okay, what jumps out at me is we know what the current flowing right here is, right? Okay, that's going to be 4 volts divided by 2 ohms, which gives us 2 amps. KCL then tells us that the current here is also 2 amps, right? Because there's nothing that separates, or there's nothing at this junction here that would cause an additional current to flow out of that node. So therefore, now we also know that the voltage, which I'm just going to start giving them random names, VA, is equal to 8 volts. Right? Okay. So now, from those two together, using KVL, I can say that the voltage from here to here is 12 volts, plus, minus, right? Stretching all the way down to the bottom, right? 8 plus 4, they have the same polarity. Now, if I were to use KVL to address this branch right here, right, we could see that the voltage going from the top to the bottom is the same, right? Those are in parallel. The 4 and the 2 ohm are in parallel with the 3 ohm and the 6 volt. So that's also 12, which then tells us that the voltage here is what? Well, I just wrote it. 6 volts, right? Because we have a 6 volts down here, and so the one above it must be 6 volts. Once we, yes?
I'm sorry. So why would that not be affected by the junction between them?
Because KVL applies to any loop.
So it could be one big loop?
The loop could be this. The loop could be something weird like that. You can take any path you want to as long as you return back to where you started from. And so this loop, which is what we're using right now, is perfectly fine. Okay, using that, we also know now that this current will be 6 divided by 3, so that will be 2 amps. Now we can combine those two currents together, and we know that this right here, well, that's a short, so it doesn't really. No, we can say that. So this current here is going to be 4 amps, right? 2 plus 2. All right, so we can also apply this KVL again to this loop, right? Yes?
How do we get the 6 volts for the 3 ohm resistor?
Because the voltage between here and here is 12 volts, 8 plus 4. The voltage between here and here is that same 12 volts, so it's 6 plus 6. Yeah?
How did you determine the direction that A was going? That the current was going in? Just from positive and negative? From the original?
So this is a question that comes up a lot. I think that, I don't know if people are really understanding the way that I think they're getting confused by when I say it's arbitrary, but you have to be consistent. I think people get confused by that. So let's say that what I did first was I defined the 6 volt polarity. Okay? If I were to go like this, well, that's not right. Hold on. Let's leave this like this. Let's say I were to define the current going in the other direction, like that. Since this doesn't obey the passive sign convention, that means that V equals negative I times R. That's what I mean by being consistent.
Okay.
So then I would be equal to negative 6 divided by 3, which would give you negative 2 amps. I think it's, to a certain point, maybe some people are making it harder than it really is. You have to pick a direction for one or the other, and then when you do the calculations, you have to be consistent. The reason why I say use the passive sign convention is because I don't want us to have to go through and each time look at the 4 different combos of the directions of V and I and then figure out whether there's a negative or not. I mean, you could do it that way if you want to, but it just seems like one place to mess up. All right, so we keep going with this one. Let's see. So we can use this loop right here because we know all the voltages in that loop. So essentially, I keep erasing stuff. Okay, so we have in this loop, this loop right here. Actually, I'm going to go ahead. I'm going to use this loop. So what we have is 6 plus 6 equals 12. So again, the voltage across the 2 ohm resistor must also be 6 volts. Which means that the current flowing here will be 3 amps. Okay, so we keep moving. We know what the current flowing here is because it's 2 amps minus 2 amps, right? So this is 0 amps flowing this way. Oh, no, it's negative 2. Okay, it's 4. Okay, sorry. That's the reason why I had the direction the other way. It was less confusing. So 4 amps flowing that way. Okay, so now what else?
You can get IAR.
Can't you, yeah, can't you find?
Oh, there you go, yeah. You can get IR already. I was trying to solve the whole thing, but I realized, yeah. So this right here will be equal to 7 amps. No.
Mine. No, no.
Oh, I'm not considering the last branch. Yes, sorry. We have to consider this branch, and this branch. So it's 3 plus 4 plus 2, which is 9. And then you could continue solving the rest of the values. Yeah.
How did we get 6 volts to 2 ohm resistor? Is it because it's like when we did the loop,
It's again just this loop right here. We know that the voltage from here to here is 12 volts. So therefore, if this is 6 volts, this must also be 6 volts.
also from that 6 volts up top and like that, all you just add the 2 volts to it. Alright.
Yeah. Okay. So are there any other, well, first off, does that make sense to everybody? We didn't go over too many problems like this. This is another method they sort of hint at a lot in the homeworks. It's just a different type of implementation.